All right. Hello, everyone. Welcome to the June program meeting for the SDAA. We've got a little bit of club news, and then I really want to just give as much time as possible to the amazing presentations that we have. We've got a couple good ones, and a big shout out to everyone that agreed to come in. Yeah, it's going to be really fun. So let me move this bar out of the way so I can control the slideshow. There we go. Um, so just some quick sort of club news. This isn't everything. So go read the reports, the newsletter that gets sent out every month. I highly recommend reading that. It's actually a really great resource. I'm amazed that there's a group of people that put that together. It's really good. Anyways, we've had another round of member engagement invitations that got sent out. Check your emails. The board, like we said last time, has created three new committees: membership, or I think we're calling them teams now: membership, events, and facilities. So if you want to get involved somehow in the club, but you're not 100% sure exactly how, just send an email to president@sda.org, or check those notices that would have been sent out. And there was a reminder about them sent out a couple of days ago as well. Um, Astro 101 is returning July 11th. The invitations for that should be going out by the end of this week. It'll be happening Saturday at Dave's house, like the last one, and it was a really good success, and I'm very much looking forward to hanging out with everyone again. Yeah, thanks, Dave, again for hosting the Astro 101. If you haven't been, it's a really low pressure, casual astrophotography time. It's quite casual. I think some people, like there's a Zach, I think Zach Walker was there, who's capturing some really good images, but most of us were just hanging out and chit-chatting and getting to talk about our passion for the hobby, and so it's really nice. One other piece of news: the events team, which is one of these three teams that was recently formed, held their first meeting, which is awesome. Hopefully, really good things are going to start coming from that. It is not too late to sign up for that team or any of the other teams. The first point of business in the events team, I was at that meeting, was upcoming in-person program meetings. So hopefully, sometime in the next month, 2 months, 3 months, we might have an actual in-person program meeting, just like the old days. I've never been to an in-person program meeting. That's how new I am to the club, or maybe how long it's been since we've done an in-person one. But that's really exciting. And if you want to be a part of that, yeah, just send a message to President of SDA, or reach out to me, or throw your name in Slack, whatever makes sense. Yeah, and with that, let me get to our schedule for this evening. I'm your host. I'm Francisco Contreras. I've got a YouTube channel around astronomy and astrophotography, but mostly I'm an SDA member and on the board of directors. And today we're going to start with, I should have, let me check. I can't see the group of people, but we should have two students from the Greater San Diego Science and Engineering Fair. Are you guys on? Where'd you go? Where's this
Yeah,
list
I'm
of people?
on.
Yeah.
Awesome. Oh, you guys are both in. Are you both in here as me? I sent you guys my link. That's why you're both in here as me. Okay. Sorry about that. The name underneath your thing says me. So, um, yeah. So we're going to start with that, and then we're going to follow with Dr. Leonard, Douglas, who's going to tell us all about Betelgeuse, which is, I feel like there was so much news and hubbub about it maybe 6 months ago when it started getting dim again, and it's sort of gone all quiet on the Betelgeuse front. So I'm excited to hear, as much information about that as we can, because there's, I think, some really cool opportunities to just take part of and experience probably once in a lifetime event. So we'll start out with actually, Brian, are you ready to get us going?
Yeah, sure.
Cool. So we'll start with Brian. Let me stop sharing my screen. And Brian was he won an award from SDAA at the Greater San Diego Science and Engineering Fair. This was back in March, and let's hear all about what he's got, what he submitted. Hey, Brian.
Hey, all right. Wait, can you guys see my screen?
Yeah, we can see that.
All right. So thank you for this opportunity first to present my work. So my project is called Space Debris Orbital Prediction using hybrid physics machine learning and space weather data. So basically, first of all, What the problem is that the world is really dependent on space infrastructure, satellites, because of obviously GPS navigation, global communication system, and the national security system overall. And these space debris collisions are exponentially increasing over time because of Kessler syndrome. And this means that when one debris hits another debris, this causes exponential increases. And this creates an overall cloud of other fragments that destroy other satellites. And an increase in satellites that's currently being done today is causing more satellites to crash into, causing the amount of debris to increase at a drastic rate that we have never seen before. So, the problems with existing methods is that NASA's current SGP-4 model that's used is very inaccurate. And this is causing optical and radar trackers to track down known objects and keep inputting to the SGP-4 model, which keeps getting more, which is always inaccurate. And this is a problem because the radar and optical trackers are currently limited to just tracking 30,000 objects because they can't just rather than looking for new ones, they're forced to just keep tracking. And also another thing is that most methods are confined at lower for LEO orbits, leaving infrastructures in these higher MEO and GEO endangered to debris. So the goal of this project was to create two proposals that balance efficiency and accuracy for debris orbital predictions, a hybrid physics machine learning model, and a dynamically updated B-star model that estimates atmospheric drag for orbital predictions. And then some challenges that we have are that the space environment is chaotic, meaning that a lot of the events that happen are very hard to predict. And this is why SGP-4 is really struggling, just because of the chaotic nature of our environment and these different environmental effects that are difficult to overall model. And also B-star, the atmospheric drag coefficient is very noisy and it's small, and small and stochastic. And this means that even small, tiny errors in the values would cause thousands of kilometers of positional deviation over time. And finally, error compounds with every step. So small inaccuracies don't just stay small; they keep multiplying with each other, and this causes thousands of kilometers in prediction error over time. So here's what I did. So first I got data. These are all open source from OmniWeb and spacetrack.org mostly. And after I got those data sets, I was able to pre-process and cross-calibrate them. And then after I did all the processing of the data, I went over to the two models. So the first model, the B-star prediction plus orbital prediction model, what it does is it uses an XGBoost model to first predict that coefficient. And once the atmospheric drag coefficient B star is predicted, it's plugged into SGP-4 and dynamically updated over time in an attempt to make predictions more accurate. So the second method that I have is this hybrid physics machine learning model. And what this does is it creates a baseline physics prediction using physics equations that we know, Kepler's laws and stuff. And then after that, what the random forest regressor does is it takes into account all the environmental effects from the data sets. And using those data sets, it's able to edit the initial path and correct it and make the path more make the prediction more accurate. And these two methods were compared to the baseline SGP-4 model. So after that, the final step was prediction and alert. So prediction, what this does is basically you just run simulations using these two models, and the prediction warns the collision and approximate time of the collision. And you can use based on these predictions, if they're accurate enough, you can use a collision avoidance maneuver. And here's some results that I have. So this is for the XGBoost B-star estimation model. And as you can see, the MSE is 0.002 approximately, and then the RMSE is 0.04, and then the MAE is 0.01. And this basically means that the XGBoost is predicting B-star well overall. But however, the problem is the MSE shows that this prediction is sensitive to outlier B star values, meaning there are some small amount of outlier values which are causing these huge prediction errors. And then here's the results of all the models. As we can see, the B-star dynamically updated prediction method performed the best initially. However, after a while, the hybrid model did better in long-term areas, and then SGP4 overall did the worst. So here's a more clear graph that we can see. So the green line is the B-star prediction plus, and then the yellow line is the SGP4, and then the blue line is the hybrid physics machine learning model. And here we could see that in the 1 day interval, which is the graph on the left, SGP4 picks up a lot of error over a small amount of time. However, the hybrid model and the B-star model are pretty similar, with the B-star method performing slightly better. And now that we go over to the right, we can see that the hybrid model performs significantly better than the other two in long distances. And then here is a heat map of the comparison by model and object type. And as you can see here, the darker it is, the more inaccurate the prediction is. So the most inaccurate would being the V-star method paired with just debris, natural debris. And overall, a trend that we see here is that natural debris, the one on the right side, across all models is the most difficult to predict. And the reason for this is because natural debris has weirder shapes and they're not like similar. Like payloads and rocket bodies are universally similar across all types, so they have a similar movement in terms of moving in space. However, since debris doesn't have a similar shape, the model has more difficulty predicting for it, meaning that because the it moves differently in space due to the different drag effects. And here's the collision avoidance. It's a proof of concept. And as you can see, the satellite path, the initial one is yellow, and then the debris orbit is the red one. And this was predicted using the hybrid physics machine learning model. And using this conjunction point that was discovered, we were able to make a new path, the green path, which allows the satellite to not collide with the debris, which it would originally do. And some key findings that I'll summarize is that the B-star estimation plus orbital prediction model wins within around 24 hours because it directly corrects drag before errors accumulate. But when the errors start to accumulate, it starts doing bad, which is when the hybrid physics machine learning model picks up and overall does better in long term. And then another thing that I noticed was that object geometry emerges as a model independent limiting factor, as irregular debris shapes produce unpredictable drag that no propagation method can fully compensate for. As we can see that the natural debris was the most difficult to predict. And then in conclusion, so just some conclusion points. This novel ML-based orbital prediction framework targeting the MEO and GEO, a critically underserved by existing research region, was mostly successful as we could perform collision avoidance maneuvers based on the predictions. And the B-star estimation plus orbital prediction model had good short-term predictions, but long-term it failed. And the last one is future work. And future work is just expand to multiple solar cycles and validate against operational conjunction data for collision avoidance applications. And another thing that's necessary is the area to mass ratio, which affects objects in MEO and GEO orbits a lot. And that is like some research that I'm gonna have to conduct, but it's part of my future work. And then for this, potential global impact is protecting billions of people, so safeguarding the GPS communications and natural security systems through accurate predictions, and then minimizing Kessler syndrome effect, enabling autonomous satellite safety, as future satellites can self-protect using AI-driven forecasts, and this reduces human intervention and response time from hours to seconds, and it allows for the scaling to millions of untracked objects. All right, thank you for listening.
I have some questions for you, Brian, if you don't
Yeah.
mind. First of all, that was an awesome presentation. That this is like really interesting stuff. And if any of the members have questions as well, please free to, throw them in the chat or what have you. So can you tell us a little bit about yourself? Where do you go to school? Like, what's your are you what what grade are you in?
Oh yeah, so I go to Scripps Ranch High School and I'm a rising junior.
Nice, dude. That's awesome. Um, how did you find this? Like, how did this become interesting to you, or like, how did you come across this topic specifically?
Oh yeah, so basically, I wanted to do so I had previous machine learning and AI skills, and I just really wanted to apply it to a field that I have a lot of interest in. So I was like, I'm interested in astronomy and I have these AI skills just lying around. How could I really make use of them? And I was like, maybe I could create um AI algorithm that could solve a problem. And this is
Yeah.
where I found space debris and just found it was a huge problem that I could use my skills to possibly contribute a good model too.
Nice, man. How much hardware did you need? Like, how did you train? Is it a model that you actually trained yourself, like you, or
Yeah.
the
Yeah.
so how much hardware or tokens? I'm not really sure. Like, well, how big was that effort?
Oh, so like the data set? Or
Yeah,
oh yeah. So I think so the data set was trained on over 100,000 distinct orbits. So it was a huge data set.
yeah.
And it was on over 20,000 distinct objects.
Wow, that's pretty cool. Awesome. Does anyone else have any questions for Brian? Let me check the chat now. Oh, we got a question from Bob. How long did you run the program, and is it ongoing? Like, how long did it take to run, and are you is it ongoing?
Oh, so it's currently not ongoing, but I could turn it on and it can directly pull from just satellites around Earth and then pull data about on different debris and run predictions on them. So it could be ongoing right now. It's currently not ongoing. The training itself took around 8 to 12 hours overall.
Whoa, that's pretty cool. Did you train it locally or like on a cluster somewhere?
Oh, locally.
Nice. That's pretty cool. Awesome. All right. Well, Brian, thank you so much. This was a great presentation. I'm glad that we were able to to get you an award. And yeah, I think you're a lot of kudos in the chat. So thanks, man. I really appreciate it.
Thank you.
Yeah. Okay. I think next we have Vishwas. Are you still on, bud?
Yeah, yeah.
Awesome. Hey, man, how's it going?
Good. How are you?
Good. All right. Feel free to share your screen and jump
Sure.
into
Okay.
it. Yeah.
Keep going then. Okay. Let me put this in the slideshow. Okay. So, yeah, my name is Vishwas. I'm also a rising junior at Scripps Ranch High. Friends with Brian. So, yeah, my project was basically using ML and basically neural network architecture to have a spatial and temporal prediction and classification of solar flares to further evaluate risk on aviation technologies like HF blackout risks and additional details that I'll be going into right now. So it's basically a roadmap that I'll be following, but the project itself was divided into two phases. Phase one, of course, was the extraction of the temporal and spatial data that I needed. And for the LS, so the models were basically built so that it was a LSTM plus CNN fusion. So the JSOC was the standard for JSOC was a source that I queried all the data. Sorry.
Oh, sorry. Hold on. Let me get him on mute.
Okay.
Yeah.
So yeah, the Joint Science Operations Center, I believe, that's the acronym. That's where Stanford stores all these live data that's coming in, and that's where it has all these sharp data products. And I used both the text and magnetograms, and I was able to label them according to what flare they are using the SWPC records you see on the right. And that was phase one, basically making the LSTM and CNN model and fusing them for a solid prediction of the flares itself. Now, phase two was using those flares and using those outputs from the LSTM plus CNN model to evaluate the risk on HF blackouts, on the GPS the disturbance, and these were used by basically combining them with space weather drivers like the negative BZ component, KP, the DST, and these are all gathered from the GOES and the NOAA. And the TEC was based on this, and yeah, so the total electron count was also a driver that was used. And of course, all of them were clean, synchronized, to build a kind of real-time plot that you see on the right. This is a sample plot that is interactive and shows, based on the flares, how much risk there is for the aircraft, whether it be from the HF blackouts or GPS disturbance. And red kind of signifies, um, of course, the most risky, and then green and blue is red is much better, as you see on the index on the right. And this is basically proven, of course, because flying over a polar region means there's more exposure to kind of the material that you see. So the electron content, whatever it may be, is much lower on the lower latitude regions. And so my idea was, why not, have a better way to predict it much better? Because right now, solar flares are a major problem, as solar activity itself unleashes kind of so many things into the upper ionosphere right now that affects aircrafts, and that can be lacks in communication and GPS disturbances that kind of really harm the way we can get things done right now. For example, the hurricane relief communications failure happened in September 6th of 2017. So in the middle of a hurricane, when we needed the communication happen between the aircraft carriers and whatever destination they were supposed to go to, there at the same time there was a massive X-class solar flare, and because of that, there was a HF blackout so high, HF blackout that was so high that they couldn't cross communication perfectly, and that led to a really delayed response. And the 2003 Halloween solar storms was also another instance where these series of solar storms caused a blackout in HF, the high frequency blackouts, and kind of the GPS disturbances that we see in aircrafts. So, of course, every flare stores magnetic free energy, and that basically every single time a flare happens, that stored energy kind of releases or bursts out, and the heliosphere is majorly where that kind of magnetic field travels through. And of course, when that magnetic field is southward, it can combine with the northward component of the planet. So what happens is the southward field can cause reconnection on the Earth's atmosphere, which leads to all this electron continent flooding the upper atmosphere of Earth itself, and that leads to all these risks that we face. So this is the data coverage of the entire project, starting with phase one, of course. So the prediction horizon I used was 24 hours, and the CNN magnetograms themselves were 6,690. But of course, each of those magnetograms had three components: BY, BZ, and BX, and BT, sorry, BR, BP, and BT. And 314 Hartmans is basically a grouping of these of the CNN data, the magnetograms that I used. And for the LSTM data, for the temporal data, I used nine sharp scalar features at 120 second cadences. And this right here is my train and validation splits, as you hear. And now the parameters itself, these are the nine parameters that the Sharp products have. So the Sharp C720 data product use these parameters, of course, because these are the main things that measure the magnetic potential that the sun has. So tot pot, and then US flux, all these are kind of how much coiling there is on the surface of the sun, because of course a flare conventionally means coiling and shearing at the surface of the sun releases large amount of energy, a large amount of magnetic field. And these are kind of the more this is kind of a more in-depth visualization of the different sharp parameters that we have. And the target samples for this, for phase one, of course, the CNN and LSTM predicting these kind of flares were X-class and M-class flares. So these are the most major class of flares that heliophysics researchers have to deal with, because these are the most catastrophic. Anything C-class and below is, of course, not as harmful. It's basically negligible. And you see there's some differences, some heavy spots on the X-class flares and M-class. There's still a lot of noise. This is a relatively low M-class flare, but these are kind of the similar noises you see on a conventional magnetogram. And the way you can read these on the SWPC records is on the type, we often look for X-ray. And in X-ray, there's the category. So B, C, these are all from June 17th, which was a record I saw online, I believe today or yesterday or midnight, sometime like or something like that. And these are all low flares as you see, but it's a problem when these say X of class 4 or 5 or M of class of 20, even it can go up all the way to that. So, of course, again, the forecast horizon was 24 hours and the prediction window followed that. So, starting with the LSTM, my results initially, of course, for the baseline were 0.499 to zero point 0.5, and that was the first test I ran without any atom optimization, without any of the proper ML techniques, including the ReLU architecture or the deeper 32 frame grid in the convolutional 2D architecture. So that kind of course, that is expected, but that was kind of a random guess because zero point 0.5 means it's just guessing at that point. It's just like labeling randomly M or X. But then I used further optimization using this architecture where the first layer was hidden at a 128, and then the second layer was better than that, and then it followed a ReLU architecture to learn the more non-linear features, and then it also followed atom optimization to reduce the prediction accuracy in terms of prediction itself, and that kind of helps a lot. Using the ReLU and the atom optimization were the most conventionally like helpful LSTM ML methods. And that finally brought my results back to 0.681 to 0.924, which was considered successful for the LSTM model. And this is the precision recall curves and the results you see here. Overall, pretty successful for the LSTM portion. And now these were the multiple iterations that I went through after that. And now moving on to CNN. The product itself was again the HMI Sharp C720s, and these were extracted again from the JSOC. And these were magnetograms, each with a BR, BP, and BT vector. And the CNN architecture was pretty similar, except of course, it used a convolutional 2D architecture, was a convolutional neural network. And additionally, I started with using the ReLU optimization this time. And yeah, so the standalone results, the area under the curve was 0.803, and the average precision was 0.558, considering overall, so indicating overall the success of the CNN alone. And now, basically, what researchers do often, instead of combining the models in training, I use regression to combine their outputs to make a unified model. So this way, instead of having to use a 3D convolutional architecture, we can simply use an LSTM and CNN architecture to make the spatial and temporal model that we aim for. And that's what I tried to do here. Instead of combining two models in the training, I combined their outputs to using regression to make a unified and solvable. And this was the fusion equation that I used, kind of visualization to picture it. And after the fusion, it produced very positive results. So the average position was 0.706 and the area under the curve was 0.930. So it proved that the LSTM and CNN can be combined to make an overall successful spatial temporal model. And then these were the overall results compared to each other. The LSTM did perform better than the CNN, but that's because of the data product that was being used. LSTMs run off of not just magnetograms and they're not convolutional networks, so they can train better off of numerical data using the actual data inside of the FITS file stored that's stored astronomical data. And that was the reason of more success. And these are again the results of the individual baselines for the LSTM, CNN at their best, and then the fusion at the weakest of 0.429. And that was basically because of mismatch and the inability to clean out the NaN or undefined values. And then fusion at its peak was the promising results, and at its best was the one you see here, 0.930 for area under the curve, and average precision was 0.7, as we've covered before. And then now phase two was I basically used those outputs that I got from the two models, from the spatial temporal model. And using that, I was able to build an aviation risk. And now that was basically combining the X-ray flux, KP, the DST, the southward BZ, of course, the solar speed, and one of the most important, the total electron content. And these are all space weather drivers that can help diagnose kind of the risk you're having on the aviation technology. So HF blackout risk, these are all from formulas that are necessary. And southward BZ, as I've explained before, is, of course, when it combines with the Earth's northern facing magnetic field, it kind of opens space. That's called reconnection, that allows these total electron content to increase. And that's what leads to the effective increase in high frequency blackouts and GPS disturbances and all such things. And this is basically the overall risk score that I was able to calculate. So every single time risk score is calculated, this is the algorithm that follows. And basically it weights each of these things accordingly. The radiation proxy is weighted a little less, but of course the HF blackout and GPS disturbance are going to be higher on risk, and that's why they're weighted more. And this was a risk timeline that I was able to generate using the decade I trained. So as you see, there's some spikes very rarely that go all the way up to 0.6 or beyond. Of course, because a major like solar storm, like X20 class flares, would be rare. So that would happen. But you see the majority is centered around 0.4 often, or there's a flat line around 0.4 and then often going below to near zero and instances like that. And that checks out. And then this was the 2017 solar storm event, and you can see the risk score here is just all over the place, bouncing up and down, and then spending a lot of points just on the top near the 0.4 area. Of course, the solar storm had a direct effect on these. And then, so basically, what I was able to find that lines with common knowledge right now is polar routes, of course, have a higher risk because they're less shielded. There's more electrons flowing through them, and that even that hurricane event that I explained before, that was an aircraft that was flying through the polar regions. And when you come lower in the lower latitude regions, as you see here, of course, there's more blue and much wider and bigger blue and green areas as opposed to the polar routes. And of course, and then along with that, I was able to formulate a reroute probability based on how much risk there is, because if all along the path there's more reds than there are greens, of course, you're going to need a reroute. And that reroute probability is formulated using this equation. And then these were again, the 2019 to 2010 to 2019 overall kind of risk score map that I generated. And that one is what I showed before. And then this was the storm simulation again. So the polar flight, of course, has a much higher risk score, as you see here, 0.5. It's spiking there. And then the whole trend of the mid-latitude flight lower than the polar region, of course, is following that kind of lower risk score centered around like 0.3, 0.4-ish. And yeah, and then this is the plot I showed for clearly outlining where there's green, where there's blue, and of course the polar and lower latitude regions accommodate that. And these are the overall kind of results that I was able to achieve. And so basically now the next step and limitations for me was that this project effectively does predict based on the patterns that was learned during the multiple hours of ML training and whatnot, but there is a necessity there for real-time data coming in from the JSOC and FWPC. So my next step is, of course, getting an API or some service that pulls up that live data to make more accurate predictions, because, of course, beyond this decade, it won't be able to predict the next accurately. And that was pretty much it.
That's pretty cool, Vishwas. You said you need it like ideally you'd have like API access. So that's not something that you use to gather all this data that you used for training?
No. Yeah, so I did gather, no, like what I meant for gathering the data was just live data at
Yeah.
the target prediction window. So I gathered all the data over a span of like multiple days, just
Yeah.
using there was a package called SunPy, and it
Okay.
has all the data, or it has all the cells that automatically query the JSOC data and OASWPC records, and that ran for a while. It does take a lot of time, but once I was able to extract that data, I just ran the model to train off of the patterns in that.
Yeah.
Now, once I have the patterns, I need the live data pulling in to kind of keep it consistent.
Yeah. Cool. That's pretty cool. Well, thank you for your presentation. I don't know if anyone in the chat has, yeah, Bob's saying this needs to be a real-time application. Yeah, it'd be cool to see it on your like flight tracker status or whatever.
Yeah.
Like that'd be kind of cool. Um, cool. Well, thank you very much, and again, congratulations on winning that award in the science fair. Keep up the good work, Ben. I think you and Brian both. I think you guys have got some really cool stuff to look forward to. So thanks again for coming and presenting to us. I really appreciate it, and I'm sure all of our membership does. And if you're ever interested in doing astronomy or astrophotography or solar imaging or whatever, come join the club. We do have student pricing, by the way, so it is pretty cheap for
Mhm.
students to join the club. I'll send you guys an email after the fact, and yeah, you guys can join the club. It'll be cool. All
Yeah.
right.
Thank you.
Hey,
Yeah.
Francisco, if I
Yeah.
could
What's
put
up?
in a quick
Yeah. Go ahead.
plug, I've been doing this for a lot of years now, and the quality of the science projects at the science fair is just so much better than we've ever seen before. It's incredibly competitive. We had 5 judges. We need interdisciplinary judges because there's a lot of neural network modeling and so forth. Um, and if you think you got snowed by a quick presentation, you actually get a little over a week to review all of the material before the judging.
Yeah, so that's Kin's attempt to get people to want to go be judges. For anyone that isn't aware, we give cash prize. The club gives cash prizes to, some of the participants,
Yeah.
and the judging panel is made up of the membership. So if you've got interest, if you like Kin was saying, multidisciplinary is really good. Yeah, next time you see probably when are you gonna start looking for judges, Kin?
Probably as soon as the science fair, gives me the call, then
Yeah,
I'll announce judges. And when was it? In March, April
yeah,
timeframe.
okay.
So
So
that's generally the thing.
for next February, March, April, somewhere in there, if you get an email for all the membership, if you get an email about being a judge, you get to come look at this work. And like you said, you get about a week to really digest everything before you go in and rattle off a ton of questions to Brian and Vishwas. So, all right, thanks, guys. Um, Next up, we've got a presentation from Dr. Leonard. Doug, are you ready over there?
Sure am. Those are tough acts to follow.
I know, isn't it awesome to
Well,
see like
I
these
can
kids are in
say
school?
I've never had as one of my talk conclusions protects billions of people.
Yeah.
So whatever I'm about to talk about is going to be a letdown after that.
No, I'm sure it'll be great. Yeah. All right. Well, the floor is all yours, Doug.
Okay, let me see if I can get this going.
We can see it.
Okay. Oh, and I'll get fancy here and try to get a laser pointer. There we go. Okay. All right. Well, thank you very much for inviting me here to give a presentation. Um, and let me also just thank the San Diego Astronomy Association for really all the great work that you do in support of public outreach here in San Diego for astronomy. One of my roles at SDSU is as the public outreach coordinator. And so I'm constantly interacting with the public and hearing great things about SDAA. And I have to say, sometimes we get a request for a star party, which is way beyond what we can handle, and I point them to you. So some of your business is coming from me, and I can't thank you enough for all of that. All right, so I'm going to start here with a hopefully straightforward question for a group of astronomy buffs, and that is to just ask who recognizes this pattern of stars. This doesn't work as well over Zoom as it does in a live in a live setting. But of course, what you were looking at is an asterism. not a constellation. You are looking at the asterism known as the Big Dipper, which is part of Ursa Major. And we can play this game again and ask who recognizes this pattern of stars. And in this case, it is Orion the Hunter. This is one of the only constellations where, even with my limited connect the dot ability, I think I can actually, when I look at it, I can see the shape that it's supposed to be. And for that reason and many others, this is actually my favorite part of the sky. And the main reason is that it hosts my absolute favorite star in the whole sky, which is arguably the most famous star in the whole sky. And you probably know which one I'm about to point out. It is Betelgeuse. And why do I love it so much? Well, it's red. That's neat. It's extremely bright. And it's gonna explode. And this evening, I'm going to tell you why we think this is, what it means, and if you're really lucky, maybe even when to look up. So I thought I'd get into this subject by actually telling you a little personal story about how I personally got interested in the subject of tonight's talk. And that's because if you'd asked me to give a talk anytime in the last 25 years or so, it would have looked quite different than this. It would have been a talk that had something like this as a title, all about stars that had already exploded, what kind of stars they are, how they explode, what is the mechanism that drives these things to explode. And if you don't believe that that's the kind of talk you would have gotten, I don't know how many old timers there are here, but I dug up that I was your banquet speaker in 2014, where you got a much younger version of me giving you a talk. And I even found the title slide, which was all about hunting for so-called supernova progenitors, trying to
That is an amazing find, Doug.
Yeah, it took me a while, but a lucky grep, and I found it. So in all of these talks, I would have treated you to data that are taken from, some of the world's greatest observatories that we have, many high above Earth's atmosphere. And all of this was, done in an effort for my own particular research to try to reveal the secrets of very distant exploding stars, which are known as supernovae. But a momentous event happened a few years after I gave that talk, and maybe you can figure out what this event was when I tell you that this is me and my two boys atop Snow King Mountain in Jackson, Wyoming. And this was in August of the year 2017. Anyone remember what that month and year? We are just moments here before the great solar eclipse of 2017, which swathed across the United States. And I loved this experience, made for lifelong memories. And also, my kids even got to meet an astronaut, which I quickly learned was much more impressive to them to meet an astronaut than to live with an astronomer. But for me, the profound discovery that I had was it was really cool to actually see something with my own eyes that I could share with my kids and also the public as well. And it occurred to me that everything I'd ever studied in astrophysics at this point had required the world's largest telescopes to collect the data and tease the information out of it, because these objects were so remote and faint. And most of my research had been involved with trying to tease information out about exploding stars after they had exploded. And I thought, wouldn't it be fun to actually study something that you don't need the largest telescopes in the world. You can literally just point up in the sky and say, that's what I study. So it was a year or two after that I decided, I think I'm going to try to study Betelgeuse itself. And silly me, I thought it would be easy to study something, the 10th brightest star in the sky. But it turns out it's hard to study the faintest things in the universe, and it's hard to study the brightest things in the universe. And I have a year of my students' lives to attest to this fact, because it took us over a year to configure the instruments at San Diego State Small Observatory, Mount Laguna Observatory, to actually be able to observe such a bright object and get meaningful data out of it. So it took us over a year to actually wrestle things into shape to start getting data on Betelgeuse. But it turned out that the timing of things could not have been better, because just as we were coming online in early 2020, it became clear that Betelgeuse was doing something really funny. And something weird was happening to our favorite star. And some of the headlines that were around back then were even suggesting that something very significant was about to happen. They kind of built things up to a fever pitch, which even got kind of ridiculous after a while. And there were even some unscrupulous people who were trying to profit from all the excitement. But to understand why the idea of Betelgeuse actually exploding in our sky would lead to such excitement, you only have to go back almost 1,000 years ago to the year 1054. In fact, July 4th of the year 1054, because it was on that particular night. Let's hope this media works.
Imagine the night when that colossal stellar explosion first burst forth.
Stars do explode. We know this. And if one as close as Betelgeuse is to us would actually explode, it would be simply amazing, not just for astronomers. Suddenly replacing Betelgeuse would be a point of light that is about as bright as the combined light of a quarter moon. And it would be clearly visible during the daytime. It would cast shadows at night and just get everyone's attention. So how did we get to this point in early 2020? Why were astronomers getting so excited? And why, after all of that, did it not explode? The press, of course, likes to get clicks, but by May of that year, they sort of were getting the picture that maybe it's not going to explode, and it didn't. But I'll just say 3 years later, they started getting excited again. So let's talk about what it is that gets the press so excited, and then also give you the best scientific answers we have to the questions about, when will Betelgeuse actually blow up? To kind of set the stage for that, I want to remind most of you that our place in the universe here, among this retinue of planets that we call the solar system, is not the entire universe. We sit inside a vast stellar system. It's known as the Milky Way galaxy. It contains over 100 billion stars that we've learned are just like our sun. All the stars are bound together by gravity. Our sun kind of sits out around like here, okay? And it orbits the center of our galaxy. We estimate it takes about 250 million years to make a galactic year around the center of our galaxy. And you'll notice, of course, this is not a picture of the Milky Way. It's a portrait drawn by a hired artist based on our best guess of what our galaxy would look like if we could get outside of it, turn around, and snap a picture, which we've never done. Never been able to send a spacecraft far enough away at this point, because the distances are just so vast. And to give you a sense of the vastness, I always like to start with the closest astronomical object to us, the moon. Yes, it's a place we have gone to, and hopefully we're going to go there again pretty soon, fingers crossed. Of course, the moon shines because it bounces light from the sun to the Earth. It's about 200,000 miles away. And it turns out that's about the distance that light travels in 1 second. So every time you're looking at the moon, you're seeing light that left it 1 second ago. So you're looking back in time about 1 second. You might say it's 1 light second away, though people don't usually say that. Moving on to the sun, it's a big self-luminous ball of hot gas. It gives off its own light, and it's about 500 times further away than our moon is. And if you do the math, that means it takes the sun's light about 8 minutes to reach us. So you might say it's 8 light minutes away. And as I already alluded, astronomers have figured out that our sun is just the nearest example of a star, way closer than all the other ones. The closest other star to us is this one, which we call Alpha Centauri. And it takes light from Alpha Centauri about 4 years to reach us. So again, you're seeing this star in the sky about 4 years in the past. So when we return to this collection of stars that we call the Milky Way, you can see why we've never traveled outside of it. From end to end, it's probably about 100,000 light years across. We sit about 30,000 light years from the center, and the most distant, remote spacecraft that we ever sent from planet Earth is the Voyager 1 spacecraft launched in 1977, and it's currently still less than 1 light day away from planet Earth. So not even close. Don't hold your breath for an actual picture of our own galaxy from outside of it. That said, we're in a great perch to look out at the rest of the universe. And when we do, we find that it is littered with galaxies, billions of them, each containing upwards of 100 billion individual stars. This is the closest galaxy to us, a major galaxy to us, I should say. It's the Andromeda galaxy. It's about 2.5 million light years away. And it's the closest big galaxy to us, but we certainly haven't stopped getting pictures of ever more remote galaxies, each containing upwards of 100 billion stars, of which a very small fraction, estimate 1 out of every 400 of those 100 billion stars, will end its life by exploding. So not every star does it. Our sun isn't going to do it, we think. And that might not sound like a lot, but once you work out the math on it, if there's over 100 billion stars in a typical galaxy like this, 1 out of 400 is the type that ends its life by exploding. In round numbers, you come up with a conclusion that a big galaxy like this should have an explosion once per century or so. And in the observable universe, a star explodes roughly once per second. We don't see all of them, but these days we do discover thousands per year. Once in a while we get lucky and we get a supernova, an exploding star in a nearby galaxy, and see if you can spot it. This is a picture of the Whirlpool galaxy, probably about 23 million light years away. And this picture was taken in the year 2011, and the galaxy was happily minding its own business. And just to make sure you know what you're looking at, these things are stars in the Milky Way. So maybe hundreds to maybe 1,000 light years away. And then plastered in the background here is the combined light of 100 billion stars, 23 million light years away. And it was one of those stars that in 2011 decided to explode. And I'm going to show you a picture now of the same galaxy after the explosion and see if you can spot the supernova in it. Got to compare the two pictures. And if you're having trouble, we'll just blink them and that'll make it real easy. Here's the before, there's the after. Before, after. That is the supernova, 23 million light years away. So if we see these things all the time, why do we get so excited about Betelgeuse? And that reason is obvious. Instead of 23 million light years away, it's probably about 500 light years away. And what's so special about Betelgeuse, well, we've been studying it for centuries, and we now understand that it is exactly one of those very rare stars that will end its life by exploding. In fact, we call these stars red supergiants, red because of their color, supergiant because it's a humongous star, both in size and in mass. And first, if you're wondering how big it is in size, I like to compare it to something we know, the solar system. This is a bird's eye view of our solar system, the sun and the retinue of planets going around it. And if we were to superpose Betelgeuse on top of this, it would actually swallow up all the planets out to Jupiter. It's that big in size. And we know this because it's one of the very few stars that we've actually managed to resolve. It's not just a point of light. We can resolve the surface of it. And I'm kind of hiding from you the actual image of Betelgeuse taken. This was in 2019 before it started misbehaving. So it's huge in terms of size. It's also huge in terms of mass. Most estimates place it at about 20 times the mass our sun has. So it's a big star, very massive, and it gives off a tremendous amount of light. Its total luminosity, the amount of light it gives off, is about 100,000 times the luminosity our sun gives off. And stars like Betelgeuse are very rare. As I said, about 1 out of every 400 stars that nature produces will ever progress to this supergiant state, at which point they are poised to explode. How do we know? Put simply, we've seen it happen. We have seen stars explode in other galaxies where we have pictures of the star before it exploded and after it exploded. I'm going to show you, because this is the kind of work I had done quite a bit of before I got interested in Betelgeuse. This is a supernova from 2008 called 2008 BK. It's one of the closest supernova of the last 20 years, only being 13 million light years away. And this is a picture taken with a fairly ordinary telescope. And the little black box here, I'm going to show you a zoom in taken at very high resolution while the supernova was bright. So this is a much higher resolution image. And this is the supernova. And you can see all these other stars around it. Okay. And luckily, very good pictures had been taken of this exact part of this galaxy in the years before the star exploded. They weren't as high resolution as this, but they were taken in multiple filters. So they're actually color images of the star field. So let me show you a fortuitous picture that had been taken of the same field. And it looks blurry because it's not as high resolution. But, you know, this star and this star is this star and this star. You can start matching things up, okay, in the images. Much blurrier because it's not high resolution. But right where the supernova now sits, this star sat. And the more we study that star before it exploded, the more we realize it looks exactly like Betelgeuse. It is a red supergiant of about the same brightness Betelgeuse is. It has the same luminosity as Betelgeuse. And if you don't believe that that star blew up, what you do is after the supernova, you wait several years till all the fireworks go away, and you get a third picture, and you have to show that the star is gone. Because if it didn't blow up, it would still be there. So this is one of the very few cases. We only have this for, at this point, a dozen or so explosions where you have the before, during, and after pictures so much like this. So this tells us observationally that these red supergiants do in fact explode as supernova. This is the kind of work I did a lot, generally painstakingly using Hubble Space Telescope images and so forth to study the so-called progenitor stars of supernovae. Bottom line, we keep finding its red supergiants that explode, the same kind of star that Betelgeuse is. And so you can see why the prospect of studying one of these stars before the explosion was so exciting to me. It's just sitting there beckoning us. So we have great observational proof that it's worth watching. When is the big event going to happen? And why did folks get so excited about it multiple times over the last 6.5 years? To understand that, we have to delve into the heart of the matter. And by heart, I mean the core of stars' lives, to understand why some of them wind up exploding. And the way to think about a star's life, like our sun or like Betelgeuse, is I just think about it as a war between gravity and some other force. Gravity always wants to pull a star together or pull anything together, or would love to just crunch everything into a black hole. That's gravity's ultimate victory. But while a star is alive, this big ball of gas, there's a very strong force pushing out against gravity, keeping it in equilibrium. And the force is a lot to do with light itself. Light exerts a pressure. Photons of light actually exert a pressure on atoms. And as long as a star is generating light, it can actually stay puffed up and push out and resist the ineluctable pull of gravity and keep the star nicely puffed up. But it can only do that so long as it has fuel. And the basic source of fuel in every star, beginning their lives, is hydrogen. Hydrogen, if you remember your periodic table, it's the very simplest element, has one proton in the nucleus. And basically, when our universe began 14 billion years ago or so, there was hydrogen and not much else. So all stars basically are just balls of hydrogen gas bound together by gravity. And what's so simple is it's just one proton in the nucleus, sits atop the periodic table right there. And what's happening in the core of every star when it begins its life is it's massive enough to get hot enough in the core, which means those protons are moving fast enough that occasionally two of them experience a head-on collision and get close enough together to actually overcome their electric repulsion and stick together. And ultimately, when they jam together like this, they create the next heavier element on the periodic table, which is helium, that has two protons in this nucleus. And every time that happens, light is actually produced. And when billions of atomic nuclei are doing this every second, a lot of light gets produced. And that's the secret to a star's life. So long as nuclear fusion, the fusion of atomic nuclei, is happening in the cores of stars, they can stay puffed up. The problem is that you run out of hydrogen at some point. Heavier elements like helium can fuse, but they need ever higher temperatures to do it. The more protons there are, the more electric repulsion, the higher the temperatures have to be to get fusion to happen. And so once the core of a star is done with hydrogen, it has to get hot enough to fuse helium. For stars like our sun, that's going to happen. It's not going to happen for another 4 billion years or so. We're plenty of hydrogen left. But that process then fuses helium into heavier elements, namely mainly carbon after that. But for stars like our sun, and really for 399 out of every 400 stars, that's the end of the line. Their cores never get hot enough to fuse elements beyond carbon. And so that's the point where they're going to die because they can't fuse anything else. And stars like that, like our sun and like the vast majority of stars, don't have a dramatic death. Over thousands of years, they puff out their outer layers, losing a lot of their mass, by the way, in this process. And then the core of the star just sort of shrivels up and compresses under gravity until a new quantum mechanical force is found that resists the compression. And what's left of the star compresses into something like the size of the Earth, very dense, something called a white dwarf, is the ultimate end to the lives of almost every star that nature produces. Our sun, in fact, will ultimately end up as one of these white dwarfs. We see thousands of them now, the stellar corpses. 1 out of every 400 stars, though, gets born with so much mass that it can actually fuse elements beyond carbon and oxygen. But 2 points need to be made. First, when they begin fusing helium into carbon and oxygen, the temperatures in these stars, these very massive stars, get so incredibly high, and the fusion rate goes up so much that in the battle between gravity in and pressure out starts winning. And actually, this is the stage where the star puffs up because there's more pressure pushing out. And that is what swells the star up to these gargantuan supergiants. And when you see a supergiant star like Betelgeuse, you are witnessing a star that is nearing the end of its life. We know it's used up the hydrogen, and that part of the life is about 90% the life of a star. And so we know we're in the very final stages for such a thing. It's at least fusing helium into carbon and oxygen. Once those elements get formed, unlike the case for the lower mass stars, these stars don't stop there. Their cores are so hot, they can actually fuse all the way up to this element, iron, element 26. And at that point, quantum mechanics gets in the way and says you can't get any more energy out of nuclear fusion once you've gotten an iron core. And so that's when these stars come to the end of their lives. But they don't do it gracefully. Basically, the iron core gets so massive, and since no more fusion can come out of it, gravity ultimately is going to get its victory. And when it gets to be about maybe 1.5 times the mass of our sun, the core, it implodes. It gives up, and gravity wins. And in less than a second, the entire core goes from something maybe the size of the Earth down to something about the size of San Diego. And the electrons get squeezed into the protons, basically, to form neutrons. And you get the birth of something called a neutron star. But that halts the collapse. And then the rest of the star, with nothing to support it anymore, falls in catastrophically, smashes into the neutron star, and then a shockwave develops that somehow ejects the envelope out back into space. And that's the birth of a supernova. There's a lot of mystery in how that happens, but we know it happens because we see it all the time. And this infalling matter now gets expelled, and with a optical brilliance that for a time is over 1 billion times more luminous than the sun. And this is exactly the fate that we think awaits Betelgeuse, just like we think it awaits every red supergiant. The problem is the timing of the event. We know by virtue of the fact that the star has swelled up to become a supergiant, it's done fusing hydrogen. But that's about all we know for sure. The problem is it can fuse helium for 500,000 more years. And so if it just started that, we got another 500,000 years to go. Okay. After helium is done fusing, every successive stage goes faster and faster. Okay. For carbon and oxygen, maybe 1,000 years till it's going to die. If it's fusing neon, maybe 6 months. If it's fusing silicon, it's got maybe a day left. Okay. If only we could see into the core of Betelgeuse, we could give a much better timing for when this thing's going to explode. All we see is the surface. Naturally, we get very excited if the surface starts doing something weird, and that's exactly what happened in 2020. So here's the story of what got people so excited. people have been watching Betelgeuse for thousands of years, and going all the way back into 1800s, um, when photography was developed, it was recognized that Betelgeuse actually changes its brightness quite a bit. It's not constant in the sky. And for the past 100 or so years, we've been keeping very careful track of how bright Betelgeuse is in the sky. And I can show you, courtesy of the American Association of Variable Star Observers, a plot of Betelgeuse's brightness in time in the years leading up to 2020. This is what's called a light curve. You're probably familiar with these. This is the light curve of Betelgeuse over time. And you can see it varies quite a bit. Any guesses for what this gap is every year? Why was no one observing Betelgeuse? Same time every year. Hint, it's the time of year we're in right now. It's the summer.
Yes, so
Betelgeuse,
behind the sun.
yeah, it's behind the sun. It's out in the daytime. So historically, we don't have much data when it's out in the daytime. But in 2019 and leading into 2020, this is what I've hidden from you. Betelgeuse started doing something really interesting. It started having a catastrophic drop in brightness, literally all the way down to about 1/3 its normal brightness. I mean, it went from being the 10th brightest star in the sky to like the 30th over the course of just a few short months. You could literally look in the sky and tell something was wrong with Betelgeuse if you were used to looking at it. This is a little video I got somewhere. This is kind of what happened to it over those times. And it was that incredible dimming that led to all of the hyperbolic speculation that went on into February of 2020. By the end of the month, when it hadn't exploded, the press was getting pretty antsy about it. I like this one. Biggest cosmic explosion since the Big Bang, spotted in distant galaxy. No, sorry, it's not Betelgeuse. By May, they actually had the bright idea to interview astronomers. They interviewed me for this article. And boy, were we Debbie Downers on this whole thing. So this article that interviewed me here, any day now or night, the red supergiant is expected to explode and go supernova. Any day that is within the next 100,000 years or so. So they were getting the message that what we saw happening on the surface might not be telling us a lot about what's happening in the core. Just because the surface was doing something weird might not be telling us anything about the core. Remember all those progenitor stars that we had studied, known supernovae that had pictures of the star prior to the explosion. In none of those cases did those pictures show the star behaving wildly in the years leading up to blowing up. So we didn't have evidence that a big dimming of a star precedes its explosion. So theory and observation were beginning to cast doubt that this dimming was telling us anything about the imminent demise of the star, especially when its brightness then just returned back to where it always had been. This was the dimmest Betelgeuse had ever been in the 100 years that we'd been taking data. So it was very impressive. Since 2020, it's kind of just resumed. It kind of recovered from that. And it was in 2023, the press got excited when it became the dimmest it ever was. They got excited when it became the brightest it ever was. And this time, though, they were a little more cautious in their titles. But, it's exciting when it gets really bright. It's exciting when it gets really dim. But in fact, it just sort of returned back to normal after that. So what does this portend for the great Betelgeuse? If I had to be absolutely truthful and I wanted to be as conservative as possible, I would say Betelgeuse is going to explode in the next 500,000 years. I'm pretty confident about that. If you forced me, I would say probably in about 100,000 years. There's some evidence from some studies of the star that it's a bit through the helium burning phase. That's unfortunately the best I can do for you. On the other hand, keep watching it, because it wouldn't surprise me at all if it blew up today, which would mean it actually blew up 500 years ago. So just remember, it could have already exploded, and we're just still waiting for that information to get to us, and we have no way of getting it ahead of time. In case you're wondering, why did it get so faint? This took a while to work out, and believe it or not, part of the answer was revealed by data we'd taken at Mount Laguna Observatory. Happy to go into details if you want me to, or just invite my former master's student, Bobby Baljoki, to give you a talk, because this was his master's thesis. Essentially, the data we got, and again, I won't go into this unless you want me to, these are spectra we took using a spectrograph at our 40-inch telescope. And you don't have to know anything really about spectra to notice that 3 of them look pretty similar, and then 1 looks really different. And it's actually this difference that is very sensitive to the temperature of the surface of Betelgeuse. And it tells us that during the Great Dimming, the surface temperature had dropped considerably by several hundred Kelvin. And that was responsible for some of the dimming, but it couldn't explain all of it. And for that, a more dramatic event has now been implicated. It's thought that Betelgeuse experienced a giant eruption from its surface. We don't fully understand why stars do this occasionally, but basically a huge chunk of Betelgeuse's surface was blasted off, and it left the star with a large, cooler surface area under the blasted off material. Okay. And that material that got ejected cooled and formed dust grains that then obscured our view of Betelgeuse for a while. And that was responsible for a lot of the dimming that we saw as well. It was probably a combination of these 2 things that explains the dimming. As I said, we don't know exactly why the star did this at this time, but what we do know from studying other red supergiants is that this does happen. It's not unprecedented. We study other red supergiants, and we've witnessed similarly deep dimmings for them as well. If you want to see the entire light curve of Betelgeuse up to present day, there it is. And boy, it's a very variable star. There is no doubt. And if you're curious, for 2 things. First, note that these gaps don't seem to exist anymore. Guess what? Really, really brave people observe Betelgeuse now during the day. You can do it. They get photometry during the daytime of a star as bright as Betelgeuse. So we've actually managed to fill in the summer gaps that existed before. And you'll notice there is sort of a periodic dimming and brightening, and you can kind of see that this has a period of roughly a year. It's actually like about 400 days. It's thought that that is actually the pulsational period of Betelgeuse. It actually expands and contracts a bit. And that's what's causing those undulations. There's a longer period that you can kind of see here of about 2,000 days, or about 6 years or so. And that's a long period variation that is seen in data going back over 100 years. And just in the last few years, the explanation for that most astronomers have come around to now, given the evidence, is that Betelgeuse is actually a binary star. There's actually a second star there, orbiting essentially inside the outer atmosphere of Betelgeuse. It's given us lots of data that convince most of us that it's actually a binary star. There's some radial velocity data that show Betelgeuse being tugged to and from us, towards us and away from us by this companion star. There's this light, there's the 6-year period in the light curve. Most recently, this star plowing through Betelgeuse's atmosphere basically produces a wake in the gas. That has observational consequences that have been measured as well. And there's even a picture of this star, though it isn't great, but an attempt to actually isolate the picture. It's not at very high significance, but it's thought Betelgeuse is actually a binary star. I'll also say, just to add to more mystery about Betelgeuse, it's actually believed that Betelgeuse might have been a triple star system and that it already swallowed one of those stars. And it's probably going to absorb the second star in the not too distant future, maybe 10, 20,000 years from now. So really interesting system, but we don't think any of this has anything to tell us about when Betelgeuse is going to actually explode. So for that, we're left with our understanding of red supergiants nearing the end of their lives. And boy, we wish we could look into the core and just see exactly what was happening right then. So to answer the question, when will Betelgeuse explode? Keep looking, because it really literally could be tomorrow or not for 100,000 years. And what made it so dim in 2020? Giant eruption from the surface of the star that eventually formed dust that obscured our view of the star for quite a while, also leaving a cooler patch exposed on the photosphere of Betelgeuse. So that's some of the reason why Betelgeuse is my absolute favorite star in the night sky. Keep looking at it. If you notice it suddenly got a billion times brighter, send me an email right away, and you'll get credit for having discovered that it finally exploded. All right, I'll stop there and take any questions that anyone has.
Heard
Thank you
various
so
different
much. Go ahead.
explanations or just, if you will, ideas about how bright in the sky it will be when it goes supernova. What is the reality if and when it goes supernova in our lifetimes? How bright will it be in relationship to our sun?
Yeah, it will be as bright. Okay, I had my students calculate this once. If it's a classic, it's called a type 2 plateau supernova that come from these red supergiants. If it's a classic one of those, then it should be about as bright as the combined light of the quarter moon. It will still be a point of light in our sky. Don't expect to see an expanding ball in our sky. It'll just be Betelgeuse, but much, much, much brighter. And like I said, totally easily visible during the daytime, just like the moon's visible during the daytime. It will remain at that brightness for about 3 or 4 months. Then if it behaves like we think it will, this kind of supernova plummets very quickly in brightness. So like it'll dim by like a factor of 20 over the course of a couple of weeks. So it'll go from being visible in the daytime to being well visible at night, and brighter than Betelgeuse is today, but much dimmer. And then it just sort of slowly fades, eventually going beyond naked eye detection after several years. And so if you go look at the spot in space where that supernova in 1054 exploded, you now need a telescope to see it. Though civilizations all around the globe noted the explosion. So much so that from Chinese astrologers, we know the exact date exploded. It's a great day for Americans, July 4th. What better day to have a stellar explosion? Didn't mean anything in 1054. But civilizations all over the globe noted that explosion. And I think a similar thing would happen here. Betelgeuse is even closer to us than the supernova that gave us what's called the Crab supernova.
We've got a question in the chat from Jim asking about the color. So what color will Betelgeuse be when it's exploded?
So the color of these stars change a lot throughout the explosion. So basically, when a star like this explodes, the initial thing is it's called a fireball, which basically means it is completely opaque, meaning you can't see through it. It's not transparent. And in the very early days, the color of the star is an extremely good indicator of the temperature of the star. The hotter a star is, the bluer it is. And if it's really hot, I see the color of the supernova will be white. Yes, in its very earliest stages, we call it white hot, because stars or anything over a really high temperature um, gives off roughly equal amounts of all the colors of the rainbow.
Yeah.
And the human eye interprets equal color as white. Take a prism and disperse it, you see all the colors. As the supernova cools, though, and it cools very rapidly, it will go from being white to blue. Okay, really hot objects are blue. Think of a flame, the bottom of the flame is blue. And also, I could point out in the constellation of Orion, kind of paradoxically, a red color indicates a very cool temperature for the surface of a star. A blue color actually indicates a much hotter temperature. Rigel down here is a much hotter star on its surface than Betelgeuse. Betelgeuse is hotter in its core, but its surface is really cool due to the expansion, actually. So the color of a supernova goes from being white in the very, very early times to blue to ultimately red. And then when it gets even cooler than that, the light begins peaking at infrared wavelengths. In fact, Betelgeuse is so cool that it is brightest actually at infrared wavelengths beyond the wavelengths the human eye can see. It peaks out in the infrared. So white to blue to red to then eventually
Infrared.
eventually infrared, and then
Yeah.
eventually it stops being opaque. And at that point
Yeah.
it becomes a nebula and you can see through it.
Wow. We've got quite a few questions in here. Any thoughts on T Corona Borealis?
Oh, T-core bore. Yeah, I'm
Is
not
that
gonna
is that
predict.
how you all refer to it internally as T-core bore? That's
Yeah,
cool.
T-core
Thanks.
bore. Yeah, I'm not making any predictions about that thing because you get burned making predictions. You really do. I mean, when I saw the original prediction, and I know the guy who made it, I was like, "Wow, you're putting it out there," because you know the evidence that it was going to uh, do its thing, have a nova explosion, not a supernova, a nova. Um, it's based on some historical data, similar to kind of this, the idea that it had dimmed a lot or gotten a bit brighter, I forget which, and historically it had done that right before it went nova. So they went ahead and made a prediction. All I'll say is historically it's a recurrent nova. It does go off pretty regularly, but I would never, say it's going to go off this month. But yeah, I'd be surprised if it didn't in the next 10 years, but I'm not gonna stick my neck out and say it's gonna happen on a particular day because we don't really have that long a data set for this thing. I mean, it's not a recurrent nova on a year time scale. It's longer than that, but it'll be really fun when it does.
Yeah.
But the predictions came and went just like they did for Betelgeuse. Is it too bright for JWST? That's a great question. The answer is yes, unless you do something special. And astronomers are very creative. I had to get very creative to observe it with the 40-inch telescope at Mount Laguna. It helped that we had a really crappy spectrograph that had terrible throughput. So the terrible throughput actually helps us in this case, ironically. I don't know if JWST has observed it. You could Google that and see. Yeah, it's difficult to observe things this bright with such sensitive instruments, but like I say, astronomers are very creative in how they make these observations. I'm not, yeah, other than getting the spectrum out at long infrared wavelengths, I'm not sure what we would learn um, necessarily from JWST, but
Yeah.
it is great at getting long infrared spectra. So that alone would be really interesting.
And that chart you showed was, you said it was AAVSO data,
Yeah.
which is like a member-led organization, right? Like we can join AAVSO and learn to be
Hmm.
variable star observers. Actually,
Absolutely.
they have tutorials on their site. So if you want to participate in actual citizen science that ends up in a graph like this being presented by such a smart man as Doug, like you can join AAVSO and contribute to the data sets. It takes a little bit of effort, but it's doable. So uh, when you say, email me if it suddenly gets really bright, that's not necessarily too far away from the truth, right?
That is correct. Though this would be something that you would notice just looking out at the sky.
Yeah.
Yeah, we haven't had a galactic, meaning in the Milky Way,
Mhm.
supernova visible to humans since what's called Kepler's supernova in 1605.
Yeah.
I kind of think nature took note that we invented the telescope in 1608 and
So we
said,
got to
"Great,
hide these.
great, you've invented the telescope. Now you're going to need them to see every
Yeah.
supernova going forward." And we haven't gotten another one.
Yeah.
Um, the closest one was in the Large Magellanic Cloud, supernova 1987A, and that one you could see with the naked eye. Um,
Wow.
that's actually the fellow who discovered it, Ian Shelton. He developed a photographic film in those days in 1987 and saw the supernova on it and literally walked outside and looked up and saw the new star. So that's how he knew he had discovered something important.
Nice. Last couple questions here.
Sure.
Assuming a companion star, do we have any idea where it was when the dust cloud appeared? So, like, what was it?
Oh,
Would we know that if it was in the firing line, essentially?
well, that's interesting. I hadn't thought of that. We currently okay. Yes, I'll do this in real time. Let's work
Yeah.
backwards.
Yeah.
Um, it's currently behind Betelgeuse, if what we think is true is true. So
Okay.
it's currently behind it. So the Great Dimming was roughly 6 years ago, which is
Yeah.
roughly the period of the stars. So I'm going to go ahead and say it wasn't in the firing line. It was
Yeah.
safely behind Betelgeuse when it uh, blew out this chunk of its surface at us. So, yeah.
And Dennis, of course, our resident outreach coordinator and the funniest guy I've met, says when it explodes, what would happen if we called out Beetlejuice, Beetlejuice, Beetlejuice?
Yeah, I get it. Yeah. Yeah.
Yeah.
Yeah.
Thanks, Dennis.
Probably nothing, but
Probably nothing.
yeah.
That's awesome. Well, thank you so much, Doug. This was such a fascinating presentation. I really appreciate we are growing our relationship with your organization, with your institution, and we keep just getting, I think, the better end of the deal. So this has always been so good for us to get to speak to you, and this is one of our better attended online program meetings that we've had in probably the last year or two. So I think
Awesome.
something about Beetlejuice really gets people going. So
Thanks for
yeah.
having me.
Yeah, thank you so much. One last thing for all of us that are still here, if you are interested in a ticket to the San Diego County Fair, please throw your email address into the chat here. I'm going to take the list of email addresses here and I'm going to draw four names randomly. We have four extra tickets to the San Diego County Fair. The reason that we have these tickets is we're sponsoring a photography contest at the fair, and there's a special astrophotography section. We've got these four tickets. So when you do go to the fair, go check out the astrophotography section. And again, we were looking for judges a while back. If we do this again next year, we'll be looking for judges again to judge these astrophotography things. Again, Doug, I really appreciate you jumping in. And I know it was last minute. I don't think a lot of people maybe don't know the behind the scenes. I was I was like
We're scrambling.
running short. I was a little frantic, and Doug really pulled me out of a tough spot to find it, and it turned out to be one of the better presentations we've had. So thank you,
Excellent.
Doug.
Thank you.
Yeah. And this is actually the last program meeting that I will be coordinating. I've done the last, I think, 3 or 4 now, and it's now being handed off to the events team. So if you've got ideas of who should come speak at our program meetings or what sort of things should we do at them, I advise you to join the events team. They are taking the baton from me, and they'll be coordinating it from here on out. And so, yeah, if you wanna have your hands in who gets to talk to our amazing membership, go join the events team. If you need information on how to do that, feel free to reach out to me or president@sdaa.org. Other Dave will gladly point you in the right direction. Cool. All right. Well, thanks everyone. This has been a really good meeting. I'm going to grab this list here, and yeah, I appreciate everyone's time this evening.